Thank you for the introduction. Today I will talk about two topics. One is our still relatively new research wind farm, WiValdi, and the other is my area of research, which is Model Predictive Control for wind turbines and wind farms. I first want to start with an introduction of myself, as my resume is still relatively long and winding. After graduating with a master's in electrical engineering, I joined the MathWorks as a technical support engineer, a typical entry-level position at the company. In 2007, I moved to Braunschweig and I joined the DLR rotorcraft department. In 2010, my husband got an offer from Google and I moved to Mountain View in California. I stayed home, first with one kid and then with two. In 2012, I started working again, this time on the optimization of online advertisement algorithms. In 2016, we moved back to Germany and I rejoined MathWorks, this time as a technical consultant. I worked mainly on data analytics projects, also in some areas where you would not necessarily suspect the usage of scientific software. For example, I implemented a salad sales prognosis tool for a local beer garden salad manufacturer who sold roughly 500 salads. The project was a success. Here you can see me as my farewell from MathWorks, and I'm holding a Kukla salad gift box in my hand. However, I also worked on projects which you would more readily associate with data analytics or data science, including 5 projects for the wind energy industry. In 2020, I left MathWorks to join DLR and to help with the commissioning of a research wind farm. I'm also an external PhD candidate at the Hamburg University of Technology. Hopefully, I will graduate later this year or early next year. I also want to introduce my research organization, the German Aerospace Center, Deutsches Zentrum für Luft- und Raumfahrttechnik, DLR for short. DLR does research in the areas of aerospace, space, transport, energy, and security. It is the largest German research organization with more than 10,000 employees and now more than 100 institutes placed all over Germany. DLR sees itself as a bridge between academia and industry, fostering cutting-edge research together with universities and bringing that into the real world together with our partners from industries. Johannes and my institute, the Institute of Flight Systems, has sites at more than 6 locations. This is an aerial view of Braunschweig, where the institute originates from and where most of our colleagues work. It is also home of our largest test bench, the simulation center AVIS, where we can simulate the behavior of aircrafts and helicopters. We have also other test benches, including an icing tower, where we can test the behavior of helicopter rotor blades under icing conditions. We operate several helicopter UAVs. And this is the hangar which is home to some of the aircraft of our research aircraft fleet, the largest one being an A320. We also have 3 research helicopters, a Bow 105, an EC 135, and a small coax helicopter. The question is now, why should an aerospace research organization operate a wind farm? The answer is that there is simply a lot of overlap between the two areas. If you look in the middle, you see the wakes emitted from an airplane wing, as well as the wakes emitted from turbine rotor blades and from the turbines in a wind farm. This is, by the way, a very famous picture which you will also see later in this presentation, and which, if you go to wind energy conferences, you see at least a dozen of times. And then if you look to the right, you see that the motion of aircraft wings and turbine blades are also very similar, as are the materials that they are made of. This is another slide taken from a presentation of one of my colleagues from our organization Wind Energy Experiments. It shows the site of the research wind farm, which is located roughly 1 hour by car from Hamburg, which is the second biggest city in Germany. Here's also the website of our research wind farm. This is its layout. There's one small 500 kilowatt turbine, which is currently under construction. And then there are 2 big multi-megawatt turbines, which went operational in 2023. There are also several meteorological masts, so we have a pretty good idea of the meteorological conditions as well as the wind on this size. The 2 megawatt turbines, Opus 1 and 2, are Enercon E115, EP3, E4 turbines, which are rated at a power of 4.26. So they are normal industry-sized megawatt turbines. What sets them apart is that they are literally equipped with thousands of sensors. So there are sensors in the foundation, in the tower, in the bearings, and in the rotor blades. This is a list of the sensors which are placed in the first turbine, as well as a picture of it. You can see that the rotor blades have names A, B, and C, and also that there are points on the rotor blades to track their movements very accurately. This is the rotor blade mounted on a test bench to test its behavior, its modes, and to calibrate it. In the picture on the right, you can see my colleagues sitting in the rotor blades. I like this picture for 2 reasons. First of all, you can see how much cables are needed to connect all these sensors, and then also it demonstrates very nicely the sheer size of the blade. On the bottom, you see a schematic where the location of sensors are depicted as points, as well as the movement of the blade. This is an aerial view of WiValdi, of the turbines and mat masts which are already installed. If you go down in the main wind direction, you first see an IEC mast which measures the inflow to the farm. Then the first upwind turbine, as I said, it's an Enercon E115 rated at 4.26 megawatts with a hub height of 92 meters and 115 meter rotor diameter. Then we have 3 mat masts which measure the wake from this turbine, and finally the second turbine, which is identical to the first one. So normally you would never place 2 turbines in main wind direction. We do that to investigate wake effects, which are a major problem for onshore turbines, where turbines are placed closer and closer together. So we want to be able to understand wakes, to be able to mitigate the effects. First of all, they take away energy from downstream turbines, and then they actually also add loads to them. So there are 2 aims. First, ideally, we want to be able to increase the power output of wind farms by operate the wind turbines as team players, and by lowering the mechanical loads on the downstream turbines, we also want to extend their life and decrease the maintenance and operation costs. These are the control inputs that we have on the turbine. In high wind speeds, we can pitch the blades to keep the energy output constant, as well as to minimize the mechanical loads acting on the structure. In lower wind speeds, we use the generator torque to maximize the energy output. And then finally, we can also yaw the turbine to put it into the wind. This is a simulator. This UI is available on our website. What you can see on the left are the controls of Opus 1. So with the pitch, you can control the thrust of the turbine, and then you can set the yaw angle. Here, this turbine is operated at rated wind speed. You can see the power curve with the power increasing with the wind speed taken to the power of 3. And then at the rated power, the wind is kept constant by pitching, the power output is kept constant by pitching the blade. The first turbine is set directly facing the wind, and we see that the power output is at 100%. What we can also see is that the wake of this turbine covers the second turbine, and we see that its output is only roughly at 90%, and the fatigue loads are actually at 70%. Now, if we slightly misalign the first turbine, so that we have here a yaw misalignment of 5%, we see that with that we get the fatigue loads down to 60%. I want to switch gears now and talk about how we can use model predictive control to decrease the loads acting on turbines. So wind turbine control can be seen as a multi-objective optimization problem. We want to maximize the generated power while minimizing the mechanical damage equivalent loads and the actuator activities subject to actuator constraints. This is a very active area of research because the size of turbines has increased considerably over the last years, and with that the turbine tower and blades have become much more slender. Modern control algorithms have been shown to be very effective at decreasing delts. However, this typically comes with an increase in pitch actuator. I conducted an automatic Google Scholar search just to show you how much research effort goes into this. So obviously it's impossible to list all the papers, so I just listed 4 which were important for my work. One of the first papers is from David Schlipf, who investigated a collective pitch control MPC, so setting the pitch of all blades collectively. Then another possibility is to optimize them separately, so individually. And then it has been also investigated to model the turbines as quasi-linear parameter varying models. This was done, for example, by Sebastian Mulders, who used that for CISO torque control, and we extended his idea to MIMO control. This is a schematic from Wikipedia to show how MPC really works. We are at the moment at sample K, and we know that the red trajectory is the reference trajectory on which we want to stay. So what we do is we calculate an optimal control signal, here depicted as the green line, over a prediction horizon. And if we would apply that, we would end up on the brown trajectory. What we do then is that we apply the first step of this trajectory, which brings us to K+1, and then we would repeat our calculation. In practice, we very often store the trajectory that we have calculated to use it as a warm start at the next sample step. For wind turbine control, we use a non-linear MPC because the mechanics and aerodynamics depend non-linearly on the wind. Then we linearize this around certain operating points, so we really use quasi-linear parameter varying modeling. The torque control that Sebastian implemented is depicted here, and what you see here is that what it does is it really lowers the excitation of the natural frequency. So in the histogram that you see on the left, you see the baseline controller depicted as blue bars, and what you see is that it very often excites this natural frequency. However, the qLMPC, depicted in red, is able to guide the wind turbine around this natural frequency. And on the right, you see what this means for the tower displacement, so for how much the tower is moving. You see that in the blue baseline bars, they are much more often higher amplitudes, and for the MPC, they are much more often lower amplitudes. This is the block diagram of the baseline controller. The feedback signal that we have is the generator speed, and with that we first set the torque control. So this is the signal that we use to maximize the energy output at lower wind speeds, and then we also use it to set the pitch at higher wind speeds to keep the energy output constant. Now, both of these signals are replaced by calculations done with our MPC. However, what we also use is that we assume that we have good wind knowledge to set the control signals of our MPC. These are the results that we got. So the algorithm was developed by Pablo Cisneros and Herbert Werner at Hamburg University of Technology. Sebastian Mulder used it in a CISO design, and we used it as in a MIMO design. So we set the pitch and the torque simultaneously. What you see here is our excitation signal, so the wind. In the second plot, we see the tower for aft acceleration, and you see that we are able to decrease the variance of the signal by a ratio of 4.6. Again, the baseline controller is depicted in blue and the MPC design in red. And similarly, for the generated power, we look at the variance of the difference to a power reference, and here our MPC is able to decrease that variance by a factor of 18. Keep in mind that MPC is an online optimization, but we are able to converge in 2 milliseconds. The code is available on my GitHub. Now, I mentioned before that this decrease in excitation and in power variance comes at the price of an increase in actuate activity. Here are the baseline PI compared to the MPC design at different rate constraints. And on the left, you can see the baseline PI at different rate constraints, and you can see that the black, the blue, and the red line are nearly the same, just because the turbine kind of acts in this pure feedback design as a filter, and these rate constraints are never met. So what we see in the first two plots are the inputs, the wind and the control input pitch. And then we see the states, the rotor speed and the tower acceleration. And finally, the generated power output. Please note again that we do not see any difference regardless of how we set the rate constraints. What we see now on the right is that there is relatively little difference between the standard rate constraint, which is at 8 degrees per second, and the high pitch rate constraint, which is at 13 degrees per second. I chose these because 8 is really the standard, which is normally used, and 13 is what we have in our research wind farm. However, if we lower this to 4 degrees, we can see that now we get a higher variance in rotor speed and in tower for aft acceleration and in the generated power. However, it is still much lower than what we see with the PI baseline controller. It is only slightly higher compared to the much more aggressive pitch rate constraints of 8 degrees per second and 13 degrees per second. So in summary, what we could see is that MPC leads to considerable reduction of power variance, blade and tower del. This comes at the price of an increase in actuate activity. And we clearly see this trade-off that we need to decide how much we are willing to sacrifice our actuators to decrease the mechanical damage equivalent loads. Areas of future work is this was CPC, so collective pitch control. So we could move into looking into individual pitch control for this. And then this is also a very simple PI design. So it also would make sense to compare that with a more advanced design. One consideration would be to simply include a feed-forward control and to see how well a non-predictive feed-forward feedback design does compared to MPC, and then also deploy modern feedback schemes like H-infinity, for example. Another idea would be to assign monetary value to the del reduction so that we could find a sweet spot between del reduction and actuator usage. There are a few caveats. First of all, we either need to be able to estimate the wind very well or to have wind measurements available. Then, as I said, we obviously need modern, strong actuators. And then we also need a model of our wind turbines. And for wind turbines, we have that. But what if we now want to move to wind farm control? So wind turbines are grouped into wind farms to make efficient use of areas suitable for harvesting wind energy. Wind farms also decrease the cost of connecting the wind turbines to the grid per turbine, as well as their operation and maintenance costs. However, wake interaction between upstream and downstream turbines lead to considerable power loss and add additional mechanical loads on downstream turbines. So again, we have a multi-objective optimization problem. We want to maximize the generated power or keep it as close as possible to a reference power. At the same time, we want to minimize our mechanical damage equivalent loads as well as our actuator activity subject to actuator constraints. So there have been different methods suggested for wind farm control. In actual induction control, we throttle the power of upstream turbines to have more energy available downstream. And in wake redirection control, we change the yaw to redirect the wake away from downstream turbines. We use Koopman-MPC. The idea of Koopman is that you can approximate any nonlinear system with a higher order linear model. This has been done for wind farms by Casamo and van Wingerden from TU Delft. What they did was that they used the CFD tool SOFA to generate a 3D grid with 100,000 grid points, and then they flattened these points into vectors, applied Koopman lifting functions to them, and then singular value decomposition to reduce the order. From that, they built linear models and then used them in MPC. We showed in our work that we actually don't need 100,000 grid points, but that we can improve power reference tracking by using physically motivated Koopman lifting functions. We showed that we are actually really real-time capable by only using the average wind speeds at the rotor disks. Also, that if we have sudden changes in wind speed, we are able to track them with adaptive MPC. And then we showed that with a combination of wake redirection control and actual induction control, we are able to maximize power yield. And now the question that I want to answer in this presentation is what happens if we put an additional penalty weight on the yaw angle to make sure that it stays as small as possible. We used the WFSim simulation environment from Bersma from TU Delft. This is an openly available MATLAB simulation environment, which is based on linearized 2D Navier-Stokes equations, where the wind turbines are modeled as energy sinks. We used it both for open loop data acquisition and for closed loop controller tests. We always assumed that we have a constant free stream wind of 8 meters per second. And the inputs that we have are the thrust control signals of the first and second turbine, as well as the yaw angle of the first turbine. We also assume that we have the wind speed in front of the first turbine available. The states that we have are the average wind speeds of the first and second turbine, and then our output is the total farm output. These are the signals that we use to build our Koopman model. And then in closed loop controller tests, we have an additional signal. We use the grid power reference PREF. So these are results that we get in open loop. And what we did is that we ran a long simulation where we changed the yaw angle of the first turbine by increments of 5 degrees and then kept it constant for 500 seconds so that we reached a steady state. In the first plot, you can see what happens if we align both turbines with the wind. This is the centerline wind, so you can see that we take a lot of energy out at the first turbine, and then if we look at how much is available at the location of the second turbine, we see that we have roughly 4 meters per second available. In the second plot, we see that the first turbine is yawed by an angle of 20 degrees. So if we look at the energy that is available now, this is 5 meters per second. As I said, we did that in increments of 5 degrees for the first turbine, from 0 degree to 35 degree. And if you look there in blue, we have the energy output of the first turbine. In red, the one of the second, so that is increasing, and black, the sum of both. And we see that we get an optimum at 20 degrees. And this is actually 10% higher of what we get if we operate those two turbines greedily, so both aligns with the wind. So as I said, we used Koopman-MPC, and the idea of Koopman is that you can represent any nonlinear finite dimensional system with a linear infinite dimensional system. So our goal is to approximate our nonlinear system with a finite linear system. I want to show you an example where we actually are able to completely represent the nonlinear system with a linear finite system. It's taken from a Brunton paper from 2016. So we have a second order nonlinear model and with two states, and you can see that the second state, which I called V, depends nonlinearly on the first state U. So what we do is we introduce a new variable, which we call g of k, which equals u squared of k. And then if we move that ahead one step in time, we see that this would, because we have u squared k plus 1, we could just use the knowledge that uk plus 1 equals mu of uk and plug that in, and then get that we have mu square of g of k. So now we really end up with a third order linear model. So really this is also a graphic from that paper. We can now decide whether we want to go non-linearly from our original states to the new states, or whether we want to move first go to the lifted states and move them linearly forward in time. In our example, we don't have a closed form solution. So what we do is that we run our simulation environment in open loop, and we collect data for the states, which are effective wind speeds, for the inputs, so the thrust controls, the yaw control, and the wind speed in front of the first turbine, as well as our output, which is our wind farm power. And then we apply Koopman lifting functions to the state. In our case, because we are looking at a wind farm, we use square and cubic terms, which represent the force and the power. And then what we do is that we append this data, formulate our optimization problem, and we solve this optimization problem to get our Koopman matrix. So here you can see the identification data that we used. We used for the thrust controls band limited noise. Then for the yaw, we did a step sweep with added band limited noise, and we looked at 6 states, the effective wind speeds, their squares, and cubic terms. And then for our validation data, we used test signals that ship with WFSim, so noisy thrust controls, and then we implemented a stepped sweep of the yaw angle, and you can see that we end up with a variance accounted for of 84%. This is then the Koopman-MPC that we implemented. The objectives for our wind farm is that we want to minimize the error and minimize the change in turbine controls. We used the Koopman wind farm model that we built to predict the wind farm states over a finite time horizon. Then we solved the optimization problem to obtain the optimal control inputs for each turbine under certain constraints. We set those control inputs to obtain the next step, and then update our predictions and optimizations at each time step of our simulation. This is the results that we get with the baseline controller. That's an actual induction controller, so we do not change the yaw. In the first plot, we see the power output, the whole farm output depicted as a purple line, the reference power as a solid black line, and the green dotted line, that's the greedy power, so the power we get if we operate both turbines at maximum thrust completely aligned with the wind. And what we can see is that we are first able to follow the reference relatively nicely, and then the wake from the first turbine catches up with the second, and we lose the power and we fall back to greedy power. And in the third plot, we see that because this is actual induction control, we do not change the yaw angle at all. And now in our combined wake redirection control, actual induction control, we allow the yaw in the third plot to change, and what we can see now is that we are able to track the reference very nicely. As I said, we want to keep the yaw angle as small as possible, so what you can see in the first plot in blue is what you saw before, and then in red and yellow you see what happens if we add a penalty on the yaw angle. So you see that the difference to the reference increases. However, the yaw angle decreases as desired. So here are bar plots to summarize this. So our objectives are that we want to keep the yaw angle as small as possible. So we see that we get smaller there. We also want to decrease our actuator activity. So we also see that we are able to do that with the penalty. However, we again see this trade-off between decreasing our damage equivalent loads and increasing our actuator activity, or in this case, what we see is also that the error, the difference between the reference, depends on how much we are willing to sacrifice the yaw angle, which would lead to higher damage equivalent loads. So in summary, what we saw was that we are able to increase our power output by using wake redirection control. We also saw that with Koopman-MPC, we got a good variance accounted for in open loop and a good reference tracking in closed loop. Also, this code is openly available on GitHub. Future work would include using other simulation environments which model the wind turbines more as physical systems, so that we are able to investigate the damage equivalent loads. Then also to increase the number of turbines and use more realistic wind test cases. That is actually something that I'll talk about at IFAC. And then also use different techniques to model the wakes between the turbines. I also said that I briefly want to talk about projects that are ongoing in WiValdi. This so far was just simulation work. So we currently have a system identification project ongoing where we want to excite the actuators that we have. So we want to add some noisy inputs, specifically sine sweeps, to the pitch angle to be able to identify the modes of the turbines. The aim is to get better models and then to use them for better lifetime predictions. I did not talk in detail about that, but another research question in WiValdi is that we want to investigate noise. So having good noise model is very important for social acceptance of wind turbines. It's also important for efficient use of wind turbines, because at the moment the noise models are very conservative. So we know that we derate sometimes wind farms which would not necessarily need to be derated to stay within acceptable boundaries. And this is something where we hope that WiValdi can really help us, just because we have so many sensors installed that it will help improve the currently available models. So this is a simulation that a colleague of mine set up, which shows very nicely the noise carpet below the turbines as they are rotating. So in summary, WiValdi meets the research needs. So we are able with it to investigate how we can use the space that is available for wind energy as efficiently as possible. We will be able to investigate and model noise emissions and emissions, which are important for regulations. And also WiValdi will help to model and to see how wind energy can be coupled with storage and how we can use wind farm control for good grid reference control. So I now talked a lot about the how of wind energy control and wind farm control, but I also want to briefly mention the why. This is a chart that I got from the site climate.gov, which unfortunately does not exist anymore because it was taken down by the Trump administration. But what it shows very nicely is the effect of climate change mitigation policies on temperature increases in the future. And what you can see in red is the prognosed or the predicted temperature increases if there's very little change in climate policy. In green, if there's a medium change in climate policy, and in blue, if there are actually now strong changes implemented. And what you can see is that these curves actually diverge now, so in the 2020s. So actions that are taken now will have strong influence in the next decades. And obviously, efficient wind farm control is a very effective way of influencing our energy policies now. So thank you very much for listening, and I'm looking forward to your question.